This will be just really building on what I said before here, but I can't agree more with the term that Tom used, market insights. We have had and have interacted with people, I think all of us in the science field, for years and years, with people who can invent new things. And actually cool new things. You can go to YouTube and see all kinds of cool new inventions that are out there. A few of them are meaningful. And if we have to invent a lot of things and then sort through which ones are meaningful, it's going to take too long. I was recently asked by one of our board members, Greg, if I raised your R&D budget 10%, what would you do? It's always a good answer to have a question, to have an answer for that question when you get that. I told him the first thing that I would do is I would go over to my partner on the executive team who ran marketing, and I would give a third of the money to him to hire really good market insights people. Because I was a bit tired of inventing things that people didn't want. And so what we see, and the culture we're trying to build at Eastman, and I think you've heard it in a way from everyone who spoke here, just derivatives of this culture, is a culture that recognizes innovation is different than invention. Innovation is people serving other people. And if you can't understand what those people who need to be served need or want, the problems they're facing, whether as a society or as a marketplace or as an individual consumer, you can't really get the innovation there in time, and it'll take too long. Our Triton innovation, the original monomer was innovated in 1958.
So Greg, can you just, for people who don't know what Triton is, just
Triton is a polyester, and it's a polyester of a couple of things that are actually very connected to our copolyester line, which has got a molecule named DMT and terephthalic acid, a derivative of the textile industry. A new monomer, cyclohexane dimethanol, was invented and taken to marketplace by scientists in the last 10 years. The invention was made longer than I've been alive, just to date myself here.
But it's for what sorts of materials and applications?
For any kind of consumer good materials, any sort of a container that contains food, water containers that you see students walking around campus for. You would go and find housewares, dishwasher wares. It's been the fastest growing polymer that we have seen in history because it's replacing another polymer that was becoming disfavored. But that's actually not the centerpiece of the story. The story is that it was tried to be commercialized 3 times over the last 50 years. It finally made it. Now at Eastman, we talk about that as a witness protection program. No really good innovation hasn't been through the witness protection program at least 3 times in making that happen. But the reason it happened this time was 2 things coming together. A very passionate scientist, and you have to have somebody who wouldn't say no. But it was also brought together by market insights people, and actually that market insight started with a health, safety, environmental person who looked and who knew what was happening in the literature and actually ordered tests to be done on this new material that the business who was trying to commercialize it didn't order. They said, you'll need these 5 years down the road because I can see what's coming. And that person was right. That's market insight as to what's going to happen in the marketplace and how do I use that to try to guide the program. And so it's multidisciplinary, it's multifunctional, it's all those things, but it's got to stay focused on people. And that's how I think the culture of innovation, it's got to be as diverse as the people you're trying to innovate for, which means all the viewpoints, all the different cultures from around the globe, and the math and science skills and engineering skills that go behind all that as well.
All right, well, we're actually quite on track here. I'm going to move now to the third thematic area, which is the materials of the future. We've been hearing from the panel about all kinds of materials, innovation cultures. I would like everyone now on the panel to sort of think about what are the grand materials-related challenges that face society now. And I want you to feel free to liberate yourselves from your own contexts here, and actually also liberate yourselves from business requirements or from economics, but really to really think about problems for which there might not be solutions now. It's a really time to get a little dreamy about, if I had these materials, these are the things that I might be able to solve and achieve. Who will start off this one? Sriram.
So, a lot of companies now talk about megatrends, right? So these are truly megatrends transcending almost any other classifications. They're energy, health and nutrition, infrastructure and transportation and consumerism. And I think there was a publication that came out not too long ago that 96% of everything has to do with chemistry and material science. So it is going to be absolutely critical. We think of population growing by 50% of our planet in the next 2, 3, 4 decades, depending upon which prediction you want to believe. But innovation will always happen when companies or organizations realize that the society can benefit, right? If you take a pure engineer's approach, would you ever think take a dumb phone, a dumb computer, and a dumb camera, put it together and call it a smartphone, right? So it's these intersections where innovations are made. And it has fundamentally changed our lives, right? If you talk to teenagers, they were not listening anyway before. Now they have an electronic reason not to listen to anymore. Hopefully they're doing more math and science, right? So whether it is energy, if you think about energy and look at automotive as example, because we all ride in one of them, the industry has improved efficiency, if you think of horsepower per pound, by about 30% in the last 2, 3 decades. But in that period, or go back to early 80s, a hot rod was something with 250 horsepower. Right? Now you can't buy a $30,000 car with less than 250 horsepower. So we as consumers have taken that efficiency and utilized it in getting more power. And how that was done was lightweighting. Think of how much cars weighed 2, 3 decades ago and how much they weigh now. So as you move forward, if we want more power, then we have one other axis of requirements to balance or defeat, have our cake and eat it too. So it will continue. You can pick any example. You want more, even during recessions. So the big one in 2000, 2001, 2008, all of us, did anybody go down in size of your PowerPoint presentations? I submit no. We want more material, irrespective of what is going on in the rest of the world. Food, water, all of these things will require tremendous amount of materials innovation. We can pick one of the examples and dive deep, but I don't think we have time for that in this forum.
Well, Tom, maybe I can put you on the spot a bit because you brought up something that's quite interesting, the idea of innovation to reduce materials intensiveness, right. Which I think is probably some place we really need to get to. You make less materials, you're using less resource, less energy. The equation is pretty simple. So why don't we just actually focus on that slightly for the moment. I put you on the spot, so if you have something to say about that, please do, and otherwise I will open up more.
Well, I was going to take a slightly different one at it, but I think I'll continue with the car thing and say, look, cars need to get smaller. We've got new CAFE standards out there. The cars of the future aren't going to look anything like the cars we drive today. I believe that there is a future, ExxonMobil, with all respect, for the electric vehicle in the future, not for, but it doesn't look like the car we're driving today unless we find a way to come up with new materials and really take lightweight out, unless we come up with the materials that enable, new materials for inverters, new materials for motors, new materials for energy storage. Without those enabling inventions and the materials that allow them, we're not going to be able to downsize those cars. We're not going to be able to hit the kind of energy goals that we've set. So I think there is a grand challenge there.
So I don't know if I'll meet your dreamy requirement, but I didn't come with a urine joke. So I also believe that on the raw material side, considering energy is also a raw material, we need to pay great attention to how much goes in to get something out. And the companies that are going to be here for a long time are going to be the companies that pay attention to that. But also really important, I think, is when we start designing materials from at our gate one, the very early time, I think we should be designing those materials for what I call repurposing, reuse, repurposing. So we would design a material differently if we had in mind the next 3 or 4 things it was going to be in its next life, right? So these photovoltaic modules, it would be great if, in their 3rd or 4th life, they become a trash bag, right? That we can and I think that we as innovators today, we need to be thinking that way so that we get more mileage out of the materials we're making and putting less raw material and energy into the front end of them. I think, and there's a lot of place to innovate there.
So one body of work, processing, production, ends up having several incarnations in its service life, and then I imagine if you're really good at this, you're going to design also for its end of life so that it degrades well or can then be reprocessed, recycled even then, right? So.
And absolutely, and a lot of that is manufacturing innovation too. So don't get me wrong. There's a whole bunch of opportunity for process and manufacturing innovation.
My head has been looking to the left so much I have to look to the right and see if anybody has something to say over there.
So maybe just to make a few comments, I think we at ExxonMobil think that there are two grand challenges as we kind of go forward, and you guys have articulated them very well down on that end of the panel up here: energy efficiency and sustainability. And I'd invite you, Tom, to go out and look at our energy outlook that's recently published, and any of you in the audience, because it does talk about hybrid vehicles and all the things that are going to be necessary to meet the growing energy demand in the world. But to your question, Ivan, a little bit about reducing consumption of materials, I think synthetic lubricants are a fantastic example of materials that are invented now that are here and that we will continue to develop and enhance as we go forward that are going to help in that particular area. So I mentioned earlier in our discussion about Spectracin Elite, a new metallocene-based PAO. One of its applications is in industrial gearboxes, and it has a very high shear stability, which means it lasts a very, very long time. It doesn't break down, and that's one of the big issues we have with many of the conventional lubricants that are out there right now. So I always like to use the example. I fly into Amsterdam because we have a technology center over there. I get to visit there routinely. And as you fly into Amsterdam, you go over one of the biggest wind turbine farms that exists. That's an offshore wind turbine farm. And it sits out in the middle of the ocean. There are something like 200 wind turbines out there. Each one of those has a gearbox in it. And you have to go up and change the gearbox oil. And these synthetic lubricants allow that a lubricant to last a lot longer in that gearbox so that you're not going up and down this basically a big pillar with barrels of oil, gearbox lubrication material to change out the lubricant in that gearbox. So it's a great example of today we already have materials. We need to continue to develop those materials to make it last longer. And another great example is many of you, all of you most likely drove a car to get here tonight. And I would venture a guess to say that probably none of you in your history of owning that car have changed the automatic transmission fluid out. So most of the automatic transmission fluids today are fill for life. So you own the car, it never changes out the fluid in that automatic transmission. My dad was a mechanic, and he was always changing the transmission fluid out in his car. That was, 30, 40 years ago. So I think those are the things we need to continue to develop and innovate on as we move forward.
I actually did read your energy report. It's a good report, by the way. I would highly recommend it. Some of your colleagues came and talked about it as well. Here's the most critical insight that I picked up out of the report. There's a lot of things in there for yourself, but the projected largest source of new energy over the next 30 years by Exxon's projections is saved energy. Energy that we're using right now and that we're going to save by getting more efficient. So the projection's in there that there's I think a prognostication that innovation is going to happen. And CAFE standards and a lot of things we see in automobiles are part of that. But energy is used everywhere, not just in the transportation industry. Energy is used when you're in a clean room environment making those electronic devices to push air through the filters and to get the particles out of the filters. It's used in medical when you're using that. Energy is used when it's stored in a battery and you've got little plates that in between the battery to keep the battery from catching on fire, but still move the ions across filters that are there. Eastman's is just commercializing a technology right now called microfibers, which actually allows us to go to a higher performance filtration in many of those filtration systems. And it's all for the purpose of saving energy. And when you just start asking yourself rolling friction and you name all the places where a little bit of energy is lost, we have to go out and save all that energy or else we're not going to afford the energy that we need to produce because it will actually turn the corner at that level. And so to me, the grand challenge is to actually take the challenge of extend the lifetime of your product by making it more durable, get more uses out of your product by having a recycling path or an end-of-life path that's there. unleash all the creativity that our scientists and our markets and our consumers have ultimately, to really understand this is the challenge that we have. And when we take that challenge on and we're successful at it, we'll have plenty of room for the new consumers that are coming up in emerging markets to step into the middle class and to be a part of this as they go on. If we don't take that challenge, I think it's going to be a much more difficult world to live in, because there's not room for everybody to use energy at the rate at which we use it today. So we've got to find that way to do it by ways other than just turn off the lights and when you leave the room, which is what my granddad always taught me.
You know, Ivan, one thing, just to keep with the energy theme, and cars, there's still a lot of room in automobiles for lightweighting. Just one example, and then I want to talk about one other energy source that Greg mentioned at the end. Seat backs in cars, the structural components used to be steel and metal, and still are today often. But at Styron, we've developed plastics that can be blow molded and shaped and formed in a highly engineered way that can now be the structural component in a seat back in cars like Audis and perform all of the critical tasks, including crash dynamics, et cetera, very complex technical problem, and take weight out of a car. So there's lots of room in cars. But Greg mentioned the word lights at the end of his comments. Think about lighting, incandescent, fluorescent, LED. LED lighting, in my view, is going to be one of the major, it already is, and a major material science issue. Diffusing that light in the proper way through materials that have the right optical properties to handle that kind of light, which is a very energy efficient light, in a way that provides the kind of lighting that we need for the application. Housing those components in a way, in a material, generally a plastic, hard plastic, that has the right physical properties for impact, wear, non-yellowing, et cetera. So LED lighting would be one example, I think, where you can think about material science just beginning to play a big role in innovating on a trend that I think is going to be very important and dovetailed off of energy in the end, a way to, in fact, achieve something for society on the back of lower energy costs.
And I just wanted a little bit of a sidebar on LEDs. I remember it must have been about more than 10 years ago, more late 90s, when I was driving, at that time I had a little job working for National Public Radio, and I ended up getting behind a bus, and its brake light looked a little odd. And I realized that what it was an array of LEDs. And that was one of the first times I started to see these LEDs kind of out there in the constructed landscape. And then over the years, we've all had this experience. You know, you would start seeing them in other places, in the traffic lights, and in ever more places. And so one of the other things that I find fascinating about materials is how they change our landscape. They change the place where we live, the way it feels, the way it looks. And we're seeing this with these changes to new lighting technologies in much sort of wholesale ways. I actually find that to be one of the very exciting aspects of materials innovation, because it really changes the landscape that we live in. A sidebar that was, I realize. Any more comments on this idea of grand materials challenges? Before I actually open just this floor up here to all of you, if there's other questions in a sense, or another question that you really wish was among the few that we've asked up here that should have been asked. Any suggestions for that we can then spend a few minutes? You can challenge each other to ask the question and ask your colleagues to answer it.
We open up to audience to get.
Well, it's going to get dangerous because I'm going to have to open it up to the audience. I'm giving you an opportunity here. Okay, these are brave gentlemen. So at this time, I do want to open it up to the audience. Now, do we have mics that people are going to run around? The logistics of this? Okay, it's a little bit hard for me to see. I'm going to go first to Corey, just because I know his name.
I claim a special privilege having done the introduction. I'll jump in to ask the first question. Back to the core theme of stories of innovation here. A number of you talked very eloquently about the role of failure and sort of how much failure there is before you get to success.
Learning moments.
And
learning moments.
I'd love to hear specific stories of what was the most influential failure that you went through, and what did you learn from it? Because I think that's an essential part of the process, and I'd love to hear some specifics of a failure moment that was also an aha moment.
Surely, there's a good story here.
I think maybe not an ExxonMobil story, but I'll use this one because we all are probably familiar with it. But and none of the companies here had this particular item, but Post-it notes. The guys that were inventing the adhesive on that Post-it note were trying to make the world's strongest adhesive, and it wasn't. And they asked themselves the question, what can we use this for, right? So that's a great example. That's 3M. And I'm sure we have other stories like that too, but that's a well-known one by many people.
I'm going to come up a little short versus your actual request, but I'm going to give you some my thoughts on how this works. There's a right way to fail and a wrong way to fail, right? You can have spectacular large failures, or you can have a lot of small learning experiences, and that's definitely the way you want to go. Somebody once described for me early stage research as a low viscosity, high toxicity environment where things move fast but get killed easily. And I think that's really what you need to do. You want to fail early. You want to fail in a way that you haven't bet the ranch on it. So I've had some learning experiences that I'm not going to recount today, but there were things that I held on to too long, right? You've got to make those judgments. And with everything I've worked on that's been a success, usually sooner rather than later, you're onto something. And if you've been at it for a couple years and you haven't had that moment yet, you've got your answer.
I actually just want to piggyback on that for a second before I go to you, Michael. I just want to bring up the example of high temperature superconductivity. So in 1986, right, the first examples of these materials that conduct electricity with no resistance are reported, and the materials community goes berserk, absolutely berserk. The government goes berserk. These are the savior materials where they're going to change electrical technologies. I mean, this is really potentially transformative for energy for just about everything. The word superconductor makes it to the front of Time and Newsweek. I mean, this is big, big stuff, right? And question is, and a lot of research has been done, a lot of materials have been invented. You will find really boutique applications of these in satellites and so forth. Would you consider that to be a failure or a success or some combination of both?
So I think this is a classic example of getting emotional on a possibility versus the practicality of that people are willing to pay for. So sure, if you put $1 billion behind something, you can make almost any material. The question is, can you make 10 million or 100 million of those for the next $1 billion? Okay, and I picked billion not fortuitously. That's about the number of R&D dollars in the US that went behind high temperature superconductor. So we all see so many small companies, startup companies pitching things to us. I'm amazed how few of them do a total energy mass balance and an economic balance. Superconductivity was realized much early on at 4 Kelvin, and then the high temperature raised it to about liquid nitrogen temperatures, right? But examples that were being talked about was rail cars. That's great, but who's going to pay for keeping it at liquid nitrogen temperatures? That's where the energy and economic balance fails. So all of these, if you look at successes, grand successes, there's very strong science, very strong materials and balance for the planet, and very strong economic balance. If you don't have all three, it's going to not look very good. There are many things possible with material science. Not everything is practical.